Chapter 2, which we are beginning now, begins or deals with fluid statics. Well, now what do we mean by a static fluid? So we can define this by saying that a fluid is considered static if all the fluid particles are at rest or have the same velocity relative to an inertial reference. So for example, fluid undergoing rigid body motion would be considered static as well. So this fluid can either be completely still at rest, or it can be moving, but it would be undergoing rigid body motion. So we want to derive an expression for the pressure in a static field or in a static fluid. And in particular, we've got two questions that we want to answer here. And this video deals with the first question, which is, how does pressure vary with direction? And in particular, we're talking about the pressure at a point. So that's the first question, that's the topic of this video. And our second question, which will be the topic of the next video, is how does pressure vary from point to point? So we're going to do a short derivation to look at this first question. So we're looking at pressure at a point for a fluid at rest. Okay, so to begin this derivation, we are going to consider an infinitesimal, so a very, very small element of fluid and we are going to apply Newton's second law. So we're applying force is equal to mass times acceleration, and we're going to do that in the y and z directions. We're not going to worry about the x direction in this case. So let's define our coordinate system here. So we have x coming out of the page, we have y going to the right, and z going up. And our infinitesimal element of fluid is going to be shaped like a wedge. So we have a wedge here. We're going to draw this in 3D. And so this wedge is at an angle of theta. And this edge has dimensions of dx in this direction, ds in this direction, and dz in the vertical direction. Now the forces acting on this wedge are those of pressure and the weight of the wedge itself, the element itself. So the weight of the element, we could draw a little arrow here indicating W is our weight, and our weight is simply the specific weight, which is the weight per unit volume, or rho g, multiplied by the volume. And so the volume of this wedge is simply dx times dy times dz divided by 2. So dx times dy times dz would be the volume of the corresponding sort of box, and dividing that by 2 gives the volume of the wedge. And we're multiplying this volume by the specific weight, and here I want you to recall that specific weight gamma is equal to weight per unit volume. So multiplying the specific weight by the volume gives us the weight. Now what pressure forces do we have acting on this wedge? So on the left-hand face, we have a force acting here, and we have a force acting on this face right here, and we have a force from pressure acting on the bottom as well. And here we're not dealing with the front and back faces. They don't really come into this derivation. And so let's quantify or come up with some expressions for these forces. So the force from a pressure is going to be the pressure multiplied by the area. And so we can say, well, we have the pressure PS multiplied by the area across this face, which is dx times ds. So a pressure times an area gives us a force. On the left-hand side, we have Py, so that's the pressure on the y face, multiplied by dx times dz, which is the area of the left-hand face. And on the bottom, we have a pressure which we'll call Pz, multiplied by the area of the bottom, which is dx dy. And so we have these three forces due to pressure, and we have this weight, W. And so what we're going to do is we're going to sum forces in the y direction and in the z direction. So we'll do the y direction first. So sum of forces in the y direction is equal to, and so in the y direction we have P sub y times dx dz acting in the positive y direction. And then in the negative y direction, we have the component of this term right here. We have the horizontal component of this term. And so we have minus ps dx ds, which is the force, and the component is given by sine of theta. And this is all equal to mass times acceleration. So the mass here we're going to represent as density times volume. So the density is going to be rho times dx dy dz divided by 2. That's the volume of our wedge, and that's multiplied by the acceleration. So again, this whole expression here is mass, and we're multiplying that by acceleration. So that's the sum of forces in the y direction, and we can do the same thing for the sum of forces in the z direction. So again, we can take, so the z direction is vertical, and so acting upwards from the bottom face, we have this pz dx dy, acting in the positive z direction, and then acting in the negative z direction, we have ps dx ds cosine of theta. So that's the component of this pressure force from that top face acting in the negative z direction. And we also have one more force. We have the body force from the weight. So we're going to say minus gamma times dx dy dz divided by 2. And this is all equal to mass times acceleration. So mass is again represented as rho times dx dy dz over 2. So that is your mass term. And this is multiplied by your acceleration in the z direction. Now I do want to point out one little trick here, which is that from geometry, this expression right here, ds sine theta, is equal to dz, and ds cosine theta is equal to dy. So we're going to use that little geometry trick here. I'm going to make a note of that from geometry. ds sine of theta is equal to dz, and ds cosine of theta is equal to dy. So that'll come in handy when we write this next few lines. So actually when we substitute that in, we can cancel out quite a lot of things. And so when we do that, we're going to be able to cancel out our dx and dz, for example, from the first line. And so I'll write this again as, so we have py minus ps is equal to rho ay times dy over 2. So that comes from right here. And we're just canceling out the dx and dz terms from all sides. Similarly, we have from the summation of forces in x, we have pz minus ps is equal to, and here we're canceling out and doing a little bit of rearranging. We have rho az plus gamma times dz over 2. And again, that comes from this equation right here, and we're just canceling out some of our terms and rearranging a little bit. So here we have simplified expressions involving the force and the acceleration, but in this case, we're dealing with a stationary fluid. So there is no acceleration of the fluid, and so we can simplify this by saying ay is equal to az is equal to 0 for a stationary fluid. So that's our first simplification here. And then there's another consideration here too, which greatly simplifies this, which is that as the size of the element goes to 0, so remember this is a infinitesimal sized element, so it's a very, very small element, but as we shrink that even smaller and smaller, the wedge becomes a point. And when this happens, the weight term involving gamma becomes negligible. So effectively, gravity, we're saying, goes to 0, which means gamma goes to 0 as well. So When we make those simplifications, we can come up with these final expressions and say that P sub y is simply equal to P sub s. So again, that results from this term going to 0 because acceleration goes to 0. So Py is simply equal to Ps. And P sub z is equal to P sub s. So again, that occurs because this term goes to 0 because the acceleration is 0 in a stationary field. This term goes to 0 because gravity is negligible, and so we're just left with P sub z is equal to P sub s. And we could redo this derivation involving kind of go through the same thing with a wedge in the x direction, and we would find that we have Px is equal to those as well. So what is the message here? So in sum, why did we go through all this to just find that these terms are equal to each other? What does this tell us? So in sum, we find that the pressure at a point in a fluid that is stationary, is independent of direction. So we could redo that derivation with different values of theta, but we would find the same result, that the pressure at a point is independent of direction, which means pressure is a scalar quantity. So pressure acts in all directions. So we treat that as a scalar quantity. Now, one final point here is that often we care more about question 2, which is about how pressure varies from point to point. In a fluid. This video was all about how pressure varies with direction, and in the next video, you'll learn how pressure varies from point to point in a fluid.